All right, so we're going to continue looking at examples of functions that you can differentiate using the chain rule. And as I have said before, I am going to stop using this approach where I write f of x and g of x, first identify those, and then find their derivatives, and then sort of feed them into this formula that the chain rule gives us. And the reason for that, once again, is that even though it's not that long of a process, in practice you want this to go much faster than this took. And you'll see as you practice the chain rule, you're not going to need to do this. So I'm going to instead think of things in terms of insides and outsides. But first what I'm going to do is take this function. It's f of x equals 1 over the 4th root of x squared plus 6. I'm just going to rewrite that as a power function, or a composition of something with a power function. So I'm going to write f of x equals this, x squared plus 6 to the negative 1/4 power. This is the same thing as this, okay? Now, in order to find the derivative, f prime of x, I recognize this as a composite function because there is a clear inside and outside. So what is the inside function here? It would be x squared plus 6. The outside function is x to the negative 1/4. So what I'm going to do is think of this without writing things in terms of f and g. The power rule, or the chain rule, says that I need f prime of g of x. So what I need is the derivative of the outside function evaluated at the inside function. So what does the derivative of the outside look like? Well, the outside function is a power function, so I use my power rule. My negative 1/4 is going to come down, and then I subtract 1 from my exponent. Negative 1/4 minus 1 is negative 5/4. This is my f prime right here. I left parentheses because that's where the g of x is going to go. The g of x is x squared plus 6. Nothing changes with that inside function here. But then the chain rule says you also multiply that by g prime of x. So I'm going to multiply that by the derivative of this inside function, which would just be 2x. Now I simplify if I can. So the 2 and the negative 1/4, there's some cancellation that happens there. I could write that as negative 1/2. The x I'm going to bring out to the front because that's typically where you would see it written. X squared plus 6 to the negative 5/4. And that's really all I need to do. Okay? Notice that's a lot faster. If you can just see what is my inside function, what is my outside function, and sort of work through the chain rule without having to write all of this out explicitly, you can knock these out pretty quickly. Okay? Here's another one. This one looks similar to the last example we did in the first video, in the sense that it involves polynomials raised to some power, but it's also a product of two polynomials. So that indicates that the chain rule by itself is not the only thing that'll solve this for me. I'm also going to need the product rule because I have a product of two functions. So let's see if we can do this. I'm going to think of this guy right here as u, and I'm going to think of this guy as v. And just as a reminder, the product rule says that the derivative of a product of two functions, so uv prime is equal to uv prime plus vu prime. Okay? So in order to find u prime and v prime, u and v in their own right are compositions of functions. So finding u prime and finding v prime both will require their own chain rule. So let's start by kind of working with this product rule. The derivative dy dx is equal to uv prime. So u is not going to change in this first step. X squared minus 7x plus 1 to the 5th power times v prime. So now let's find v prime. V prime is the first place I'm going to need to use the chain rule. So again, looking at this, the inside function, the thing inside parentheses, appears to be 4x cubed plus x plus 4. The outside function appears to be x to the 9th. So I take the derivative of the outside function, 9. This is using my power rule, subtract 1 from my exponent to get an 8. and then keep the inside function the same, 4x cubed plus x plus 4. But then I also need to multiply that by the derivative of the inside function. So the derivative of this polynomial in here is going to be 12x squared plus 1. So far, all I have dealt with is u v prime. And again, in a normal problem, I wouldn't write all the u's and v's here, but since we're getting used to things, I'm going to highlight what's what in my answer. That's v prime right there. Okay? Now I need v u prime. So v is this 4x cubed plus x plus 4 to the 9th power times u prime. So this right here is v. U prime, let's see if I could squeeze it in here, is equal to the derivative of this, which again, using my chain rule, I take the derivative of the outside function, which would be x to the 5th, so 5 times something in parentheses to the power of 4. I've subtracted 1 from my exponent. That's the power rule on my outside function. The inside function stays the same, x squared minus 7x plus 1. And then I multiply that by the derivative of this inside function, which would be 2x minus 7. Okay? This entire thing right here is u prime. But notice how in order to find v prime and u prime, I needed my chain rule to do that. Technically, I could stop here. I'm allowed to do that. However, this is a huge mess, right? And typically it's helpful when dealing with polynomials to factor things. And in order to factor this, I'm just looking at these two giant terms here as their own terms and trying to find a common factor that can be pulled out. So notice here I have an x squared minus a 7x plus 1 to the power of 5. And over here, amongst all of this, I have the exact same expression, x squared minus 7x plus 1, but this time to the 4th power. 4 being the smaller exponent means I could factor this out. X squared minus 7x plus 1 to the power of 4. Okay? Now looking for something else that we have in common, I can take this 4x cubed plus x plus 4 to the 8th power and compare it to this same polynomial but to the 9th power. That's a common factor. Since 8 is the smaller exponent, that's what's going to end up out here. 4x cubed plus x plus 4 to the power of 8. Okay, so we have factored two big polynomials out of each of these, and now we need to look at what's left. So starting here, we had x squared minus 7x plus 1 to the 5th. I've pulled that same thing, but to the 4th power out. That would leave me with x squared minus 7x plus 1 there, okay, times 9. Now this part, this cubic polynomial to the 8th power, I have pulled that entire thing out. So that's gone, and I still have this 12x squared plus 1 here, okay? Then what I'm going to do is go to this expression, see what happened. I'm going to have this guy right here, this cubic polynomial to the 9th power. I've pulled that thing to the 8th power out, so that's going to leave me with one of those, 4x cubed plus x plus 4. I have taken this entire thing in parentheses to the 4th power out, and so that leaves me with just the times 5 here, times that binomial right there, 2x minus 7. Okay? Now what I would probably do, I don't want to spend any more time on this problem because it's really just algebra from here. What I would probably do in a follow-up step is multiply this out, combine like terms, see if maybe I can continue factoring, but I'm not going to do that here just for the sake of time. So at the very least, you wanted to pull out those two common factors for the purpose of simplifying. Okay, but let's go ahead and move on to something else. We haven't dealt with any exponential functions yet in this in this section. So let's do one that involves an exponential function. d dx of e to the power of tangent of x. Here, there's no parentheses present, but think about it for a second. The inside function here would be the tangent of x, because that's what's being plugged in to e of x, or e to the power of x. So in this case, taking a derivative, I would want to think of this as something requiring the chain rule, and e to the x would be my outside function, tangent of x would be my inside function. So the derivative of e to the power of tangent of x would be equal to the derivative of the outside function. Remember, e to the x is its own derivative. So I would still have e to the power of x, but then I plug g of x, my inside function, into that. So far, it looks like nothing has changed, and that's what we would have expected, because that's what happens with exponential functions, or the exponential function. But one thing is missing. I have not multiplied by the derivative of my inside function. So the inside function is tangent of x. From section 3.3, we know that its derivative is secant squared. And that's actually it. That's all that I would need to do. Okay? So you notice, again, if you have the derivative of an exponential function composed with something else, the result looks like the original function times the derivative of whatever that exponent was. And that's basically all there is to it. Okay? Here's another example. What we're going to start seeing here is compositions of more than just two functions. Instead of functions of the form f of g of x, we're going to be looking at functions of the form f of g of h of x. So composition of a composition. It may not initially look that way, but what I'm going to do is rewrite the way that this thing looks. So d dx of cosine squared of 4x is the same thing as this. Cosine of 4x quantity squared. Remember, the notation here means the same thing as this. Now, if you notice, I inserted brackets and parentheses, even though the original expression didn't need any of those. And the reason for that is because I have a function that is like the most inside function, this 4x, but then the cosine of that is also inside these brackets. So I have a function inside another function, which is inside another function. The chain rule works here, but we end up having to use it twice. Okay, so this is equal to, looking at my outside function, the function that's most on the outside is this 2x squared here. So using my power rule, the 2 is going to come down. 2. I'm going to end up with cosine of 4x here. But then I need to multiply that by the derivative of the inside function, the derivative of cosine of 4x. And remember, that by itself requires the chain rule. So I need to use the chain rule a second time on this guy. I'm going to have 2 times cosine of 4x. Now the derivative of this, again, using my chain rule, I start with the derivative of the outside function, which is negative sine of x, but I plug my inside function into that, 4x, and then that gets multiplied by the derivative of the inside function, the derivative of 4x, which is just 4, okay? Now, I'm going to do a couple of things here, because again, I could leave this as is, but you really want to simplify things as much as possible. And one little trig identity that would be worth remembering here, this one is very, very useful throughout Calculus 1, Calculus 2, even Calculus 3, is the double angle formula for sine. Sine of 2 theta is equal to 2 sine of theta cosine of theta. This is an extremely useful trig identity. And you notice that theta can be anything. In this case, my thetas look like 4x's. But the point here is I have a 2 times a cosine of 4x, and if we ignore that negative, we can bring the negative out here to make that a negative 4 if we want. We could think of that as just sine of 4x. So 2 cosine of 4x, sine of 4x, or 2 sine of theta, cosine of theta. We can combine that to make sine of 2 theta, or sine of 2 times 4x. Sine of 2 times 4x is the same thing as sine of 8x times negative 4. That negative needed to come out here. Or a better way of writing that is negative 4 sine of 8x. You don't even need the parentheses around the 8x technically. Okay? You really want to make sure that you're on top of your trig identities. They're extremely useful in calculus. That's kind of the main reason we emphasize them so much in trig. All right, let's take another look at another example. This is a similar one in the sense that it's a function inside a function inside a function. So for this guy, let's write this as f prime of x. We want to find the derivative of this, which I'm gonna rewrite as e to the 2x plus 1 to the 1/2 power, just to make it a little easier to see that I'm using the power rule there. So the innermost function is 2x plus 1. That I'm taking the square root of. That's the next innermost function. And then that whole thing, I'm making the exponent in the exponential function. So the exponential function is the most outside function here. Chain rule says I would be dealing first with the derivative of my outside function, which is itself. The derivative of e to the x is e to the x, plugging in the inside function. 2x plus 1 to the 1/2 power. Now I multiply that times the derivative of the inside function, which is this. But once again, I need the chain rule in order to evaluate that. So this would be equal to e to the 2x plus 1 to the 1/2 power. Using my chain rule, the outside function is a power function, 1/2 power. The inside function is a linear function, 2x plus 1. I differentiate the outside function first, so I bring the 1/2 down. Subtract 1 from the exponent, which would give me negative 1/2. Keep the inside as is. That's f prime of g of x, which is the first part of my chain rule. Now I multiply by g prime, the inside function. The inside function is it would just have a derivative of 2. Okay? So now I can cancel this 2 and this 1/2, and I could either leave this thing in exponent notation, or if I wanted to, I could put it back in radical notation, which I'll go ahead and do that since the original function was in radical notation. This is the same thing as e to the square root of 2x plus 1. This has a negative exponent, so I could put that in a denominator and just call that the square root of 2x plus 1. That's my derivative right there. Okay? So the last thing I want to do is use the chain rule to prove a differentiation technique for a specific type of function. So again, you'll recall that we have talked about the derivative for the exponential function e to the x. We have not addressed derivatives of general exponential functions. What is the derivative of 2 to the x, or 5 to the x, or 12 to the x, or anything like that? And the chain rule is the key to unlocking that rule. So here's how we do it. First of all, suppose that we're dealing with an exponential function, y equals b to the x. I stated over here that for exponential functions, we're implicitly requiring that b to both be positive and not equal to 1. Otherwise, it doesn't behave like an exponential function is supposed to. Notice we could rewrite that this way. I could write y equals e to the natural log of b to the x. The reason this thing is the same as this thing is because the e to the x, the exponential function, and the natural log are inverse functions. This and this cancel each other out technically and would leave me with the b to the x again. Now, why would I bother doing that? Well, I'm doing it so that I can exploit a logarithm property. We know that the natural log of b to the x is the same thing as x times the natural log of b. We have a rule that says that we can bring exponents here outside of that logarithm. Now, I wrote the x over here instead of over here, but it's the same thing. Okay? Now, what was the point of doing that? Well, this is a composite function, e to the power of the natural log of b times x. The natural log of b times x is the inside, e to the x is the outside. And we actually know the derivative of both of these. That natural log of b is a constant. because b is the base of an exponential function, which is always some constant. So I have a constant times x. That's actually a linear function that we're looking at up there. We know how to differentiate those. So treating this way, dy dx is equal to the derivative of this expression here. And we've done derivatives of a couple of exponential functions composed with other functions. We know that the derivative of the outside function is still e to the x. Evaluated at the inside function looks like e to the natural log of b times x. But then we need to multiply by the derivative of that inside function, the derivative of my exponent. And remember, once again, the natural log of b is just a constant. So anytime we differentiate a constant times x, we're just left with that constant. This just leaves me with a natural log of b. I'm going to bring that out to the front here. Natural log of b times e to the natural log of b to the power of x. But again, up here, e to the natural log of b times x is the same thing as y, which is the same thing as b to the x. So this entire expression can just become b to the x, and I'm left with this. B to the x times the natural log of b. That's the derivative of a general exponential function. D dx of b to the power of x is b to the x times the natural log of b. This is confirming something that we noted way back in section 3.1, which is this. We showed that if you take a derivative of an exponential function, the result is always a constant multiple of the original function. The natural log of b is a constant, and notice the derivative of this is a constant times the original function. This also can be used to confirm that we have the correct derivative for e to the x. Not that we need confirmation, we already proved it. But notice if you wanted to find the derivative of e to the x, I would be substituting an e in here for b. That would give me e to the x times the natural log of e. But the natural log of e, by definition, is 1, leaving me with just e to the x. That's our derivative for the exponential function we've already talked about. So let's do a couple of examples involving this idea. First of all, let's find the derivative of 7 to the power of x. Straightforward. I'm just using the rule that I just proved up here. So dy dx is equal to this. It's equal to the b to the x, which is 7 to the power of x, times the natural log of the base, which is 7. Okay, natural log of 7. I almost wrote b there. It's supposed to be that. And that's it. It's a constant times 7 to the x. Let's do another example with something that looks a little bit more complicated, and I want to look at this from two different perspectives. I want the derivative of 2 to the power of 5x. Now this I recognize as a composite function, right? The inside function is 5x. The outside function is 2 to the x. So I start by taking the derivative of my outside function, which according to my rule up there is 2 to the power of my inside function, 5x, times the natural log of my base, ln of 2. But then I need to multiply that to the derivative of the inside function, which is 5. Okay? So I can also write that as just 5 times 2 to the 5x times the natural log of 2. Typically, we would bring constants out to the front like that. What if I approached this a slightly different way, though? If you notice, 2 to the 5x is equal to 2 to the 5th power to the x. I'm using my power to a power exponent rule there. 2 to the 5th power is 32. So technically, even though this was a composite function to begin with, I can simplify it in such a way that makes it not a composite function anymore. 2 to the 5x is the same function as 32 to the x. And what is the derivative of 32 to the x? 32 to the power of x. Okay, well, this guy right here, according to my rule that we just proved up there, would be equal to 32 to the power of x times the natural log of 32. Now that looks different than what I have here, but is it really different? Well, the answer is actually no, because if you take a look at this, the natural log of 32 can be written this way, 5 times the natural log of 2. And why is that? Well, again, you have a property for logarithms that says you can bring constant multiples out here up as exponents here. So this is the same thing as the natural log of 2 to the 5th power, and 2 to the 5th power is 32. Notice I have a 5 natural log of 2 right here. So these two things could be combined to give me this. Then this guy, 32 to the x, we already showed is the same thing as 2 to the 5x. So this and this are the same. They look different, but they are the same function. Okay? And in one case, I needed the chain rule. In the other case, I didn't. So again, this is one of the reasons we spend so much time in algebra talking about these properties, how to simplify functions and of all different types, exponential, polynomial, trigonometric identities, all of that stuff. Because in calculus, we actually use it all. So hopefully if you were one of those students who, when you were going through algebra or trigonometry or whatever, and you were asking the question, well, when would I ever use this? Here you go. You're going to use it here. Let's go ahead and end this section here, and we're on to 3.5 next time.